everyone, in this video we'll talk a little bit about sampling variation. So what might happen if we take multiple samples from a population? Well, we'll start by reviewing parameters versus statistics. What do we mean when we talk about each one of those? We'll then introduce this concept of sampling distributions. What can a sampling distribution tell us and what can't it tell us? We'll also define standard error in this video. So let's start with an example. Data that is intended to measure an entire population can be found, but it is tricky. The Centers for Disease Control uses survey data to try to estimate features of health from samples of the U.S. population. Some of these surveys that we'll see throughout the semester include the National Health Interview Study, or NHIS, the National Health and Nutrition Examination Survey, or the NHANES survey, and then the Behavioral Risk Factor Surveillance System, the BRFSS. These health features that we're trying to estimate are, in statistical terms, a population parameter. A population parameter just being a numerical summary of an entire population. Now, our goal when we can't measure these parameters directly is to attempt to estimate them using a sample statistic. So let's look at just one example, the BFRS, or the Behavioral Risk Factor Survey. This was established in 1984 to collect data using telephone interviews about health-related risk behaviors, chronic health conditions, and the use of preventative services. This survey has gone on annually. It reaches about 400,000 households per year, so it's a fairly large survey. The data set that we're looking at here is called the CDC data set. This data set contains a small number of variables from a random sample of 20,000 responses. So we're looking at a smaller subset from the year 2000. So this data is about 20 years old. We have information on general health of the respondent, whether or not they exercise, X or any, whether or not they have a general plan for maintaining their health, whether or not they've smoked at least 100 cigarettes in the past 90 days, their height measured in inches, weight, their desired weight, their age, and their gender. Now, in order to illustrate what happens when we take multiple samples from a population, we're going to play pretend for a little bit. We're going to pretend that the CDC data set represents the entire population of American adults. So this will be our target population. We're then going to see what happens if we take a smaller sample from this. So we'll take a random sample of 60 individuals. We'll call this CDC sample. And then we'll see, well, how close does this sample mirror our hypothetical population? Now again, this is purely hypothetical. We're pretending here. In practice, we don't have access typically to the entire population data. But let's see how good we would do if we did have access to it. So a natural way to estimate the population parameter is with the corresponding sample statistic. So if we have a population mean, we might estimate that with the sample mean. Population standard deviation, we might estimate with the sample standard deviation. But samples aren't perfect. Samples aren't going to exactly represent the true underlying population. So there will always be a slight difference between the population parameter and the sample statistic. How different are they going to be? Well, let's take a look at some examples. So here is the mean weight of all adults in the 2000 BRFSS survey from our CDC dataset. This is our hypothetical population dataset. The average weight in 2000 of all Americans was 169.683 pounds. So we'll pretend for a little bit that that is our population mean weight. Now let's take a look at the sample mean weight, which we're denoting X bar of adults in our smaller sample. So this is a sample of just 60 adults. Looking at this, we have a sample mean of 173.3 in our sample. So our sample mean is off from the population mean by about 3.5 pounds. So we're pretty close. We're not exactly there though. It could be that this is a typical sample. It could be that this is an unusual sample. So what do? we'll take more samples. So I'm going to create a new sample by sampling another 60 observations from the CDC weight values. The average of this new sample is 168 pounds. Compare that to 169.6 pounds. We're not exactly there, but this sample's closer. If I take another new sample, this one's close. If I take another new sample, this one's a little off. What's going to happen if I take lots of these samples? Now, we want to do this quickly. We don't want to be taking samples by hand. We don't want to be writing code over and over and over and over to generate these samples. So here is what we'll do. Off screen, so before recording this, I generated 10,000 random samples of 60 observations each. Turns out it wasn't that hard. We'll do this in class. Before I show you the results, what do you think is going to happen? All right, Judge Judy's telling me to hurry it up, so let's see what happened. Here is what these sample means look like, and I told you that it wasn't that difficult to generate them. This line of code did it. What you're looking at here is a histogram of 10,000 randomly generated samples. For each of my randomly generated samples, I calculated the sample mean weight. Now, the population mean weight was right about 169 pounds, specifically 169.68. Look at where the peak of these randomly generated sample means is. It's right at 169. Further, you should be recognizing something here. How do these means look compared to, say, the normal distribution from the last video? This is a beautiful example of a bell-shaped curve. Interesting. So again, here's that red line, and you can see really where that population mean falls. It's smack dab in the middle of this curve. This isn't an unusual result. If we played this pretend game with another data set, we would see the exact same result at the end. Random samples tend to, most of the time, give you sample statistics that are reasonably close to the population parameter. If we look at where the majority of those samples fall compared to the red line, which is the population mean, the majority of the samples are only a few pounds off. However, sometimes we'll get weird samples. Some samples will just be unlucky. They'll either overestimate the population or they'll underestimate the population parameter. The distribution then of these sample statistics tells us what we would expect to get with repeated random samples. Most of the time, this has a symmetric bell-shaped curve. The name for this distribution is the sampling distribution. So when we refer to a sampling distribution, what we're looking at is the probability distribution of all possible values of a sample statistic. So what do those sample statistics look like over repeated random samples? Now, every statistic that we could look at, the median, for example, has a sampling distribution. Standard deviation, for example, has a sampling distribution. We will focus on just two in this course. We'll focus on the sample mean, denoted x bar, and the sample proportion, denoted p hat. We choose these two in particular because most of the research questions that we have can be answered by one of these two. In order to describe this sampling distribution, so if I wanted to look at that histogram and come up with a description of what I'm seeing in it, I need to know three things. I need to know the center or the mean of that sampling distribution. I need to know the variation of that sampling distribution, which we will call the standard error. And then finally, I need to know the shape of that sampling distribution. Now, let's talk about the standard error concept a little bit. The standard error is a measure of the sample-to-sample variation of a sample statistic. So it really is measuring how far off we expect our samples to be, or how far we would expect a typical sample to be from the true population parameter. Another way to think of the standard error is the standard deviation of the sampling distribution. So how spread out is that sampling distribution? Now let's focus on a particular sampling distribution, the sampling distribution of the sample mean x bar. The sampling distribution of the sample mean x bar has the following properties. The mean of this sampling distribution is the population parameter, or the population mean mu. The standard deviation of this sampling distribution, there's actually two forms that we might use here. If we don't know, or if we aren't willing to assume the population standard deviation, we might use the sample standard deviation S, which you're seeing here. We could also plug in the population standard deviation if that was something we had available to us. The shape of this sampling distribution is approximately normally distributed as long as the sample is what we'll call large enough, and we'll talk about what large enough means in a little bit. Let me get that cursor out of the way for you. And the population distribution is not strongly skewed. The sampling distribution provides the theoretical basis for statistical inference. It gives us some theory that we can use to help us learn about a population from a sample. Now, there are two basic methods for inference that we'll learn about in this class. The first type of question that we might want to answer related to a sample is whether or not we can find a reasonable estimate or a reasonable set or range of estimates for our population parameter. We also might want to compare a population parameter to a pre-specified or hypothesized value. Has the parameter increased? Has it decreased? Has it changed? In the next two videos, we're going to talk about methods for answering these questions in very broad strokes. So we'll outline the ideas of confidence intervals in Lecture 9 and the idea of hypothesis tests in Lecture 10. Following those two videos, we'll drill down deeper into these methods by looking at how they change for a particular type of population parameter. So in the next video, we'll start with methods for estimating a range that would contain the population parameter, and we'll call those confidence intervals. See you then.